And let me remind you of what we have been doing, which is trying to find out whether or not linear systems have solutions, and if they do, what the solutions are. So the first step is, given a linear system, write the augmented matrix which looks like A line B. So these are the coefficients. This is the right-hand side. If you have m equations and n variables to be determined, or n unknowns, then the augmented matrix AB is m, so it has m rows, one for each equation, and n plus 1. It has n plus 1 columns, one column for each unknown, and then one column for the right-hand side. You then do elementary row operations on the augmented matrix. And this carries your matrix. You start with your augmented matrix, and then you find a second matrix. This is the coefficient matrix for an equivalent linear system. This is the right-hand side. So you start with the augmented matrix of your original linear system. You end up with an augmented matrix of a new linear system. And this matrix has a simple form. Using it, we quickly find out if the original problem has any solutions. Also, we can write them down. So the whole point of the elementary row operations is that the elementary row operations are shorthand for the elementary equation operations. And we already know that the elementary equation operations don't mess up the solution set. So whatever the solutions are of the original linear system, if there are any, when you do those elementary equation operations, you don't mess up those solutions. And so if you find an equivalent linear system that you can easily understand, write down its solutions, if it has any, and you will have solved the original problem. This is the exact same procedure, just at the level of shorthand. And it's a lot quicker to do the elementary row operations than the elementary equation operations, because you don't have to keep writing over and over again x1, x2, x3, x4, and that kind of thing. So the simple form is something that's called the reduced row echelon form. And we're going to start class with a bunch of examples. So are there questions about the general overview? I understand that you may not be super comfortable doing it, but I do want you, by the end of class, to be super comfortable writing down all the solutions of a system once it's in reduced row echelon form. And by the time of the midterm exam, you will need to be accurate in going from the augmented matrix on the left to the augmented matrix on the right. Because just one arithmetic error and you will mess up all of your solutions. Okay, so let's do some examples. Okay, so we start with a linear system which has the augmented matrix 8, 3, 4, 16, 6, 8, 1, 5, 9, 9, 8, 13, 31, 21, 23. How many equations? 3. How many unknowns? 4. So 3 equations, 4 unknowns. Now, the thing is that you don't actually know whether all 3 equations are equally important. It could be that one equation is a linear combination of the other 2 equations, and so you don't really have 3 independent equations. That's the entire point of the reduced row echelon form. So we carry this matrix. We do row operations on this matrix, and we find that this matrix is equivalent to the matrix 1, 0, 0, 2, 0, 0, 0, 1, 0, 1, 1, 0, 3, 1, 1. Okay. Now, the first thing I'm going to do is, okay, first of all, how many equations are there? 3. The reason there are 3 equations is this is a non-zero row. It corresponds to x1 plus 2x2 plus x4 equals 3. This is a non-zero row. It corresponds to x3 plus x4 equals 1. This is a non-zero row. It corresponds to the equation 0 equals 1. I did not ask you whether all of the equations were true. I simply asked you how many equations there are. 3 equations. Now, these things are called leading ones because they are the first non-zero entry in the row, and they equal 1. The number of leading ones, this is for language, is the rank. So the rank of the matrix SC is equal to what? How many leading ones are in this matrix? 3. The rank of the matrix S, how many leading ones are here? 2. Now, okay, that's just language. You don't really know why you should care. Is this linear system going to have any solutions? No, because the third equation, no solution. The third equation is 0 equals 1. Never true. Okay, so that tells us that the linear system with this augmented matrix has no solution. Why do you get to say that therefore the linear system of this equation has no solution? Because they're equivalent, and that was a theorem, that when you do those elementary equation operations, you don't change the solution set. So if I have no solutions, then he has no solutions. Okay, now the key thing is there was a single equation that corresponded to 0 equals 1. This is actually a theorem. So we have, let me come back to that theorem. Let's just do some more examples. So here we have a linear system, 8, 3, 4, 16, 6, 8, 1, 5, 9, 9, 8, 13, 25, 14, 21. And this is row equivalent to the augmented matrix 1, 0, 0. Sorry, that is the augmented matrix of a linear system. And that augmented matrix is row equivalent to this augmented matrix 1, 1, 0, 2, 0, 0, 0, 1, 0, 1, 1, 0, 3, 1, 0. Okay, so we started with this. We started with a linear system that had 3 equations, 4 unknowns, and this is its augmented matrix. We ended up with this. So this, okay, technically, sorry, what? Well, for sure there's a solution. For sure there's a solution. So if I asked you to write down the linear system which had this as its augmented matrix, you would write down the linear system x1 plus 2x2 plus x4 equals 3. You would write down x3 plus x4 equals 1. And you would write down 0 equals 0. So technically, this represents how many equations? 3. There are 3 equations there. How many equations actually matter? 2. So this really is 2 equations. How many unknowns? 4 unknowns. So we have 2 constraints, 4 things we're trying to determine. We're going to get how many solutions? Infinitely many. Now, how many parameters are there going to be? If I have 2 constraints and 4 knobs, or 2 constraints and 4 unknowns, how many unknowns should be free? 2 free parameters. So number of unknowns minus number of leading ones equals the number of parameters equals 2. So you can put the free parameters anywhere you want. You can make x1 a free parameter and you can make x2 a free parameter. And then you can use the 2 equations to write x3 and x4 in terms of x1 and x2. Or you could write x3 and x4 as free parameters and then use the 2 equations to write. So if I made x1, x3, and x4 into free parameters, then I would use the equations to write x1 and x2 in terms of the unknowns, and so on and so forth. So you want to choose which variables to make free parameters basically in terms of convenience. So from this equation, I could write x3 in terms of x4. Or I could write x4 in terms of x3. If I write x4 in terms of x3, then when I go up to this equation, I'm going to have to plug something in for x4. I would have to plug in for x4 that x4 equals 1 minus x3. And then I would have a new equation in terms of x1, x2, and x3, which is my parameter. So how I choose where to make my free variables is simply in terms of how to most quickly write down a solution of this system. And we talked about this at the end of class last time. So the easiest choice is, so we have x1, x2, x3, x4. And the easiest choice for free parameters is going to be x4 and x2. So x2 we'll call S, and x4 we'll call T. So why is this easy? From equation 2, we have x3 is equal to 1 minus x4, which is equal to 1 minus T. That was a super easy equation to solve because x3 was a leading 1. 1 minus T. From equation 1, we have x1 is equal to 3 minus 2x2 minus x4. So that is 3 minus 2s minus t. 3 minus 2s minus t. Now, why is it that I didn't have to plug, I had this equation from equation 1. Why is it that I didn't have to plug x3 into this equation?
Because x3 is 0.
Because there's a 0 in the x3 column in the first row. And that's the entire beauty of this structure. The fact that you have zeros above and below the first column, below the leading ones, makes it so that this procedure is always going to make it incredibly easy to write down solutions. The structure of that final matrix, having zeros above and below the leading ones, makes it this procedure of assigning the variables that are not leading ones to be the parameters makes it incredibly easy. So s and t are real numbers. So this is the general solution. The general solution of the original linear system is that. And if you take this and plug it into the original linear system, you'll find that it solves it. If you want to write it in vector form, you can write this as 3, 0, 1, 0 plus s times minus 2, 1, 0, 0 plus t times minus 1, 0, minus 1, 1. Where s and t are any real numbers. And if you want to, you can check that this right here solves the linear system with augmented matrix AB. And these two solve the linear system with augmented matrix A0. So you remember how last time when I plugged in a solution I had numbers plus t times parenthesis equals a number? And I explained how the thing in the parenthesis multiplying the parameter had better equal 0 or it could never possibly be a solution. That will always happen. And so when you write down a general solution, if you want to quickly check, did I make a mistake, what you can do is you can write it in the general form, check that this part solves the original system, check that these solve the homogeneous system. When I say homogeneous system, I mean the system which has 0 on the right-hand side. So this is a very fast way of checking that you have a solution, and we'll be getting into more details on this soon. Are there questions? Yes?
Where did you get that equation?
What? From here. So all I did was I factored. So the question was, how did I go from here to here? So the first component is 3 minus 2s minus t. That's the first component. The second component of x is x2. The second component of the thing on the right is 0 plus s times 1 plus t times 0, and so forth. So here I wrote things in the component form, and here I wrote it in the vector form. Are there, yes? How did I what?
The second part solves the linear system with augmented matrix.
Oh, how do you have to actually plug it in and check.
So like for S and T, 0.
Oh, no. So if you take the original, okay. So the original linear system was 8x1 plus 16x2 plus x3 plus 9x4 equals 25. And then equation 2, equation 3. If I take minus 2, 1, 0, 0, and I plug it in, this is going to go to minus 16. If I plug this in, this is going to go to 16. If I plug 0 and 0 in, that goes to 0, that goes to 0, and that's 0. This one, and if I plugged this into equations 2 and equations 3, I would find that miraculously the left-hand side equaled 0. If I take this one, minus 1, 0, minus 1, 1, and I plug it in, this, when I plug it in, I'm going to get minus 8. This, when I plug it in, I'm going to get 0. This, when I plug it in, I'm going to get minus 1. And this, when I plug it in, I'm going to get 9. So when I plug this in to the left-hand side, what do I get? 0. And it's going to be the same thing for equations 2 and equations 3. So when you get a general solution, a very fast way of finding out if you messed up, because you do not want to check your general solution in that system. That's how you built it. You want to check if you messed up by seeing if you solved the original system. Because if you didn't mess up, by the theorem, you should have a solution. So this is a fast way of checking if you actually did things right. Questions? Yes?
On the right side becomes 0.
What?
On the right side becomes 0.
How does the right, I'm not, do you agree that these numbers add up to 0? Okay, that's why the right-hand side becomes 0. So I'm saying that this thing solves this linear system, and these two solve this linear system. Notice I put 0 on the right-hand side. That's all I mean. Okay, so, and this matrix is in reduced row echelon form. What that means is if there are any rows of zeros, they are at the bottom. The first non-zero entry of any row is a 1. Those are called leading ones. Above and below a leading 1, you have zeros. So this is a 1, good. Above and below it, you have zeros, good. This is a 1, good. Above and below it, you have zeros, good. This is all zeros. And the leading ones, as you move to the right, as you move down, the leading ones move to the right. That's the definition of reduced row echelon form. And there is a unique reduced row echelon form for every matrix. So if you were to type this matrix into MATLAB and ask for the reduced row echelon form, you would get that. Everyone in the class will always have the exact same reduced row echelon form. Okay, so let's just do a few more quick ones. So, (16, 5, 9, 4) 0, 0, 0, 0, 2, 11, 7, 14, 32, 10, 18, 8, 3, 10, 6, 15, 18, 16, 16, 18, 49, 27, 35, 25, almost done, 113, 104, 100, 125. Okay? 4 equations and 7 unknowns. This is equivalent to the following reduced row echelon form: 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 3, 2, minus 1, 0, 6, 4, 3, 0. How many leading ones? 3. Are any of the leading ones in the rightmost column? No. How many solutions will we have? Infinitely many. So we have 3 leading ones. None are in the rightmost column. If there were any in the rightmost column, that would correspond to equation 0 equals 1, no solution. So we're going to have infinitely many solutions. And how many free parameters? 4. We have 7 unknowns and 3 equations. Yes?
How should it matter that none of them are in the rightmost column?
Because if there wasn't one in the rightmost column, that would correspond to an equation 0 equals 1. With 4 parameters. Okay, so we write down the equations. x1 plus 2, x4 plus x6 plus 3, x7 equals 6. We have x3 plus x6 plus 2, x7 equals 4. We have x5 minus x7 equals 3. And we want to write down our general solution. So we have 4 free parameters, S, R, T, or whatever. We give them names. Where should I give the free parameters? So one way to do this is to say, which are the variables that are going to be dead easy to solve for? x1, x3, x5. So this is going to come from which equation? Equation 1. This is going to come from which equation? And this is going to come from? And the reason you're happy with this is x1, is it going to see x3 or x5? No, because x3 and x5 don't show up in equation 1. Equation 2 isn't going to see x1 or x5. They don't show up in equation 2. x5 isn't going to see x1 or x3. They don't show up in equation 3. So where must you put the parameters? x2, x4, x6, x7. So R, S, T, U. You must. OK, so now from equation 1, x1 is equal to 6 minus 2x4, which is S, minus x6, which is T, minus 3x7, which is U. From equation 2, x3 is equal to 4 minus x6, well, x6 is T, minus 2x7, well, x7 is U. Now from equation 3, x5 is equal to 3 plus x7, and x7 is equal to U. And we have R, S, T, U are any real numbers. Students routinely freak out about that column of zeros. They feel like if there's a column of zeros, somehow they don't need to worry about the x2 variable. Or they just see that column of zeros and they just stop. Right? So what I want you to do is, given a matrix in reduced row echelon form, write down the system. Remind yourself, write down your unknowns. Next to the first unknown, you can write equation 1. Next to x3, you can write equation 2. Next to x5, you can write equation 3. That's all the information you have. Everything else must be a parameter. So if you just follow this, you'll become super comfortable with it. And you can check that this is a general solution of the original linear system. Are there questions? Okay, so I need to introduce a piece of language. The rank of a matrix, here I told you what the rank was of this particular matrix. We need to have the general language of rank. So definition. Okay, so first of all, there's a theorem, which is given any matrix A, the matrix is row equivalent to exactly one matrix S, which is in reduced row echelon form. It is this theorem that allows us to give one matrix to 1,000 students on an exam and ask them to find the reduced row echelon form of that matrix, because there's only one possible answer. If we asked you to find a reduced echelon form of that matrix, there could be 1,000 different answers, and we would have to check that each one was correct. Now we have a definition. How to prove this theorem is something we can talk about later in the course. Given a matrix A, the rank of A, which is called rank A, is the number of non-zero rows in the matrix S that A is row equivalent to. In the matrix S, which is in reduced row echelon form, that A is equivalent to. So if I give you a matrix and I ask you for its rank, the first thing you do is you do elementary row operations on the matrix until you have reduced it to a matrix which is in reduced row echelon form. And then you count the number of leading ones or the number of non-zero rows in that matrix. So for example, if I asked you for the rank of the matrix 8, 3, 4, 16, 6, 8, 1, 5, 9, 9, 8, 13, and if I asked you for the rank of the matrix 8, 3, 4, 16, 6, 8, 1, 5, 9, 9, 8, 13, 25, 14, 21, you would have to reduce this to a matrix in reduced row echelon form using elementary row operations, you'd have to find an equivalent reduced row echelon form matrix for this one and count its non-zero rows. If you believe me, this has been done. So this matrix is equivalent to this matrix. And what is the rank of this matrix? What is the number? First of all, this matrix is in reduced row echelon form. The number of non-zero rows is what? 2. Now, for this one, technically, you have to do that entire procedure over. You have to do all of the elementary row operations on this and find a matrix which is in reduced row echelon form. Do you feel like you need to? When you do elementary row operations, does any information travel between columns? No. So when you're doing all the row operations on this matrix and carrying it over to here, did it actually matter whether this column was here? It did, in that it gave you this column. But if I then asked you, please give me the reduced row echelon form of that matrix, would you repeat your work, or would you just immediately say, I've already done the work? You'd say, I've done the work, and there's the answer. So what is the rank? It's 2. So this leads us to a hugely important theorem. So theorem, consider the linear system with m equations, n unknowns, and augmented matrix A, B. All right, so this is just the beginning of so I'm saying, for example, if you had the linear system with that augmented matrix, you would have 3 rows, 3 equations, 4 unknowns, and augmented matrix this. I'm just trying to speak in generality. So first of all, if rank A does not equal rank of A of the augmented matrix, then what would it mean if the rank of this did not equal the rank of this? Something must have happened. What must have happened if the rank of this does not equal the rank of that? There would have to be a what here? 1, and then of course, if it's in reduced row echelon form, that would have to be zeros. So if the rank of the coefficient matrix does not equal the rank of the augmented matrix, for sure you have a 1 in the rightmost column which has a whole bunch of zeros to its left. It means you have an equation which is 0 equals 1. You have no solution. You understand this at the level of specific examples. If the rank of A equals the rank of the augmented matrix, then there are solutions. And the number of free parameters equals, how did we figure out the number of free parameters? Number of unknowns minus number of equations, number of leading ones. That is equal to n minus rank A. Why did I say n minus rank A instead of n minus rank of augmented matrix? Does it matter? Would it still have been true if I'd said n minus rank of augmented matrix? Yeah, because I said that they're equal. Okay, so this is a big, huge, important theorem. This is the rank theorem. Yes?
Explain number 2 works.
Sorry, what?
How number 2 equals to n minus rank 8.
Are you okay with this? That the number of free parameters in the solution is equal to the number of unknowns minus the number of equations? You're not okay with that. Okay. Then we are in trouble. Because then we are in trouble. This is a fundamental thing. We had this example where I wrote down the 3 equations and the 7 unknowns. And I showed that from each equation I could solve for one variable. So from this example, the first equation allowed me to solve for x1. The second equation allowed me to solve for x3. The third equation allowed me to solve for x5. But when I solved for x1, I got x1 in terms of x2, x4, x6, and x7. When I solved for x3, I got x3 in terms of x2, x4, x6, x7. When I solved for x5, I got x5 in terms of x2, x4, x6, x7. So the key thing, the thing that you must understand is this line. Beyond this line, it's just math, right? What is the number of unknowns? N. What is the number of equations in the reduced row echelon form? It's the rank of A. Okay, so more questions? Yes?
So if you were to take the matrix like 8, 3, 4, then would the row echelon form of that be 1, 0, 0?
Yes. 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 So the question was, if you had the matrix 8, 3, 4, this is equivalent to that. Because first you would divide this by 8 and make it into a 1. Then you would use that 1 to kill the 3 and to kill the 4. And this is in reduced row echelon form. It's got all of its 0 rows are at the bottom. Its leading 1 has zeros above and below it. And if you have more than one non-zero row, the leading ones move to the right. So this is in reduced row echelon form. It looks very bizarre because it looks like a vector. In fact, it is a matrix. And if you were to ask for the reduced row echelon form of this, you would get 1, 0, 0, 2, 0, 0. Questions? Yes?
You just said if the right-hand side of the last row is 0, the other two numbers on the right-hand side should also be 0, one side, like in the matrix.
This no longer has to do with equations. This just has to do with matrices. You're saying this?
Yeah.
Those have to be zeros because otherwise it's not in reduced row echelon form. If I still had the 3 and the 5 here, this is not reduced row echelon form because there's a leading 1. And to be in reduced row echelon form, you have to take everything all the way to the end. At this point, you can stop and say there is no solution. But if I ask you, is this matrix in reduced row echelon form? The answer is no. Because to be in reduced row echelon form, above and below each leading 1, including this one, you must have zeros. So if you were turning the crank and you got this far, and the question was, are there any solutions? You could stop and answer the question. If the question was, please find the reduced row echelon form, or what is the rank, you need to keep turning the crank and use this 1 to kill the 3 and the 5, at which point you are in reduced row echelon form.
So both of them are above this one should be there.
If your goal is to be in reduced row echelon form, above and below all leading 1s, you must have 0. So this is a leading 1. It is the first non-zero entry in the row. It equals 1. Above and below it is 0. First non-zero entry, it is a 1. Above and below is 0. First non-zero entry is a 1. Above and below is 0. This is definition of reduced row echelon form. Questions? Yes.
For the second one, the number of parameters is also equal to the number of nodes minus the new one.
Yep.
It's also the same.
Yes. The number of equations in the reduced row echelon form is the same as the number of leading ones. 1, 2, 3, or 1 equation, 2 equation, 3 equation.
And do we also take care about this side?
This is, if you have this is the right-hand side on the equation. And you need to count it if you're asking about the rank of the augmented matrix. In this case, it's not.